Hello class, we're picking up talking about leucine, an intermediate species which we abbreviate HA. The fully protonated version is H2A+, and then when we deprotonate twice down to leucinate, A- is the fully deprotonated version. In the next few pages what we're going to be discussing is what to do about solving for pH once we have a certain amount of each of these species. The fully protonated, the intermediate, and the fully deprotonated. So this is a diprotic acid equilibrium. So we have two acids working here. We have the fully protonated, which can get deprotonated by water to form HA and hydronium, which we describe with Ka1. And then we have HA goes on to become further deprotonated by water to form A- and another equivalent of hydronium, Ka2. Remember that H2A+ does not necessarily need to be charged. This is just the abbreviation for the fully protonated species, and that when we get deprotonated, we are losing hydrogen and losing charge. So H2SO4 and H2CO3 are both neutral diprotic species. We would take something like H2SO4, it gets deprotonated to form HSO4-, and then deprotonated again to form sulfate SO4-2-. And we abbreviate H2SO4 as H2A+. And we do this so that once we abbreviate the acids that we're using, we can be sure that we're using our equations correctly. So let's see what happens when we have a certain amount, 0.050 molar, of the fully protonated species. And we're going to figure out what the pH is in this situation. So H-leucine plus, this is a situation where we have some concentration of our H2A plus species. So how do we handle this? Well, our H-leucine plus is going to be equal to H2A+, and that's 0.050 molar. And we can now use the equations that we just lined out to calculate for pH. So first we have Ka1 for H-leucine plus is 4.7 times 10 to the negative 3, which is a weak acid. The Ka2 is 1.8 times 10 to the negative 10, which is a very, very weak acid. It's generally the case that the first Ka is the stronger of the two Kas, given that it has a less negative value. So we're going to assume first that H2A plus acts as a monoprotic acid, and we're going to calculate HA and hydronium. We're going to do this using our standard ice tables. We have Ka1 is our Ka for this reaction, and H2A plus reacts with water to form HA and hydronium, a deprotonation reaction that forms hydronium. And Ka1 associated with this reaction is 4.7 times 10 to the negative 3. We can fill out our ice table as so, where we have H2A plus is initial concentration of 0.05 molar. HA and hydronium are both 0 initially. Our reactant goes down by x, while both of our products increase by x. And at equilibrium, we have 0.05 minus x, x, and x. So we can first make a pass at solving this equation, which is 4.7 times 10 to the negative 3, our Ka being equal to HA times H3O plus divided by H2A plus, being equal to x squared over 0.05 minus x. We ignore x, and we eventually calculate that x is equal to 1.5 times 10 to the negative 10. Turns out that is 30% of our 0.05, and we cannot ignore x. So what we do is solve for the using the quadratic. So 4.7 times 10 to the negative 3 is equal to x squared divided by 0.05 minus x. We rearrange to solve for x and then distribute 4.7 times 10 to the negative 3 into quantity 0.05 minus x. And we get 2.35 times 10 to the negative 7 minus 4.7 times 10 to the negative 3. X is equal to x squared. Set everything equal to 0. Solve with the quadratic, and we get an x that's equal to 1.32 times 10 to the negative second. That is equal to our hydronium concentration. We take the negative log of our hydronium concentration, and we get a pH that is equal to 9. What we're going to do next is see what happens if we were to then produce more hydronium. So we just produced HA at the same time as we were producing hydronium, and so in this situation, we just calculated for hydronium, which is 1.32 times 10 to the negative second molar. That also is going to be equal to our HA concentration at equilibrium. So we know that our initial HA is now 1.32 times 10 to the negative second. And that can go on and further deprotonate to form another conjugate base and more hydronium. This reaction has a Ka associated with it. That's 1.8 times 10 to the negative 10. We could do an ice table, and we would find an initial that's 1.32 times 10 to the negative second, because that's our amount of HA that we now have in solution. And we can use Ka2 to equal our products over reactants, which is going to be equal to x squared over 1.32 times 10 to the negative second minus x. And we can ignore x, solve for it, solve for this x, and test, and it's 0.01%. So great, it passes our test. So if our x is 1.5 times 10 to the negative fifth, that means that our A minus conjugate base is equal to 1.5 times 10 to the negative 6 molar, and that our second amount of hydronium concentration that we just formed is 1.5 times 10 to the negative 6. And we're going to call that H3O prime. Now, if we compare H3O prime to our initial or original H3O, we find that H3O prime divided by H3O is equal to times 100 is going to be equal to 0.01%. So we added a minuscule amount of additional hydronium. So that should help prove what I'm about to say, which is that a solution of a diprotic acid behaves like a solution of a monoprotic acid. So the second deprotonation adds very little. So the overall Ka for this reaction, we can just consider it to be Ka1. And that when we're trying to solve for the pH, when we have H2A plus in solution, we can just consider H2A plus as a monoprotic acid and solve with a standard ice table. Now, what we're going to do is skip over our intermediate species. So we just figured out what happens when we have H2A plus in solution. How do we solve for pH? Now we're going to skip over our intermediate and jump all the way over to the fully deprotonated and figure out what to do about calculating pH when that is in solution. So on page 73, we have diprotic base equilibrium. So we have an A minus that can react to form HA and hydroxide with Kb1. And we also then have HA can be further protonated to go back to our fully protonated species, H2A plus, forming yet more hydroxide, described by Kb2. So this is going to be quite similar to what we just described for H2A plus, except under basic conditions. So in this situation, A minus is going to, of leucinate is going to have a 0.050 molar solution. So here's our reaction that's of interest. We have leucinate over here that's we abbreviate as A minus. That's going to react with Kb1, to form HA and hydroxide, and that's going to be described by Kb1. We can assume that A minus acts as a monobasic species. Calculate HA and hydroxide. So here's our reaction. A minus reacts with water to form HA and hydroxide. This is described by Kb1, which is 5.6 times 10 to the negative 10. Our initial concentrations are going to be 0.050, 0, and 0. Our reactant's going to go down by x, our two products increase by x, and we get an A minus at equilibrium that's 0.050 minus x. HA and hydroxide are both equal to x. That x in the bottom right of our table is going to be our target, because once we have our hydroxide concentration, we can get to pH. So our Kb1 is going to be equal to products divided by reactants. We can ignore the x in the denominator and say that x squared divided by 0.05 is our expression. Solve for x, 1.7 times 10 to the negative 3. That passes our test by being about 0.3% of 0.05. So we now have concentrations for HA and hydroxide. Hydroxide is 1.7 times 10 to the negative 3 molar, which gives us a pOH of 2.77, which gives us a pH of 11.23, which is exactly what we're looking for. What we're going to do now is test to see how the pH might change if we calculated and included more additional hydroxide after the second protonation. So HA is an amphoteric species. It can go on and continue acting as a base again. So HA can get protonated again to get back to our fully protonated species, H2A+, which produces yet another equivalent of hydroxide. This is described by Kb2, 2.1 times 10 to the negative 12. So 2.1 times 10 to the negative 12 is going to be equal to our products over reactants, which is going to be equal to x squared divided by our new initial HA, which is 1.7 times 10 to the negative 3 molar, minus x. We ignore this x, and we get an x that's equal to 6 times 10 to the negative 8, which is 0.004% of 1.7 times 10 to the negative 3. So it passes our test. So our X is equal to our second concentration of hydroxide, which is OH prime, which is 6 times 10 to the negative 8. We compare and we find that hydroxide prime divided by hydroxide is a minuscule amount. So the amount that we produce of hydroxide that we produced from the second protonation is a small fraction of the hydroxide that we produced from the first deprotonation. So really our POH stays the same at 2.77. We're going to return now to the intermediate form, which is an amphiprotic species. So now we're going to discuss what happens to the one in the middle, HA. We've discussed just now that H2A+, the fully protonated species, can be considered a monoacidic species when analyzing it and calculating pH. If you have some amount of the fully deprotonated species, that can be considered a monobasic species when evaluating its concentration and solving for pH. But when we have the one in the middle, the intermediate form, a little more work is required. So leucine, HA, is between Ka1 and Ka2 if you're going from the fully protonated species and you're producing hydronium all the way down to the fully deprotonated. If you're going in the reverse direction, you travel through Kb's in order to reach up to the fully protonated species. So previously we calculated the pH starting with H2A+ or A-. But now what we're going to do is begin from HA, the intermediate form. Here is how we do this. So, example 12, what is the pH for leucine, which we describe as HA, where HA is equal to 0.050 molar? The acidic reaction that HA is a part of is HA reacting with water to form A- and hydronium. That's described by Ka2, 1.8 times 10 to the negative 10, which is here. So HA can act as an acid to form A-. The base reaction that HA can participate in is reacting with water to become protonated to form H2A+. That produces hydroxide. That's described by Kb2. So that's HA here reacting to form H2A+. Now, is the solution likely to be acidic or basic? Well, Ka2 is greater than Kb2. So if there's a battle between which direction A is going to react in, Ka2 is a greater number. It has a smaller negative exponent. So it's more acidic than it is basic, slightly. Both of these numbers are very small. But HA can slightly react better as an acid, so we would expect this solution to be slightly acidic. Now I'm going to introduce a new equation here, which is an equation describing how to reach the hydronium concentration of an intermediate form. Now the first thing that you may notice is that it all involves Ka's. Ka's can be reached through the following relationship. So first, HA is described by an acidic reaction to form A-. What we just said also is it's described by our basic reaction to form H2A+. Well, we can describe that Kb2 as Ka1 using the autoionization expression. So Ka1 times Kb2 is equal to Kw. So if you took Kb2, 2.1 times 10 to the negative 12, and multiplied it by 4.7 times 10 to the negative 3, you would get 9.9 times 10 to the negative 15, which is something we did in class, and that value is just about 1.0 times 10 to the negative 14. 9.9 rounds up to 10. 10 times 10 to the negative 15 is the same as 1 times 10 to the negative 14. So, using that relationship, everything in this expression can be written in terms of acid, and that is really useful mathematically. So, you can use Ka1 instead of Kb2 using the relationship Ka1 times Kb2 is equal to Kw. So, here we have the square root of Ka1 times Ka2 times the concentration of HA plus Ka1 times Kw divided by a quantity Ka1 plus HA. When we plug in all of our numbers, we have hydronium is equal to 4.7 times 10 to the negative 3 Ka1 times 1.8 times 10 to the negative 10 Ka2 times our concentration of our intermediate form, which is 0.050 molar, plus 4.7 times 10 to the negative 3, which is Ka1, times Kw, 1 times 10 to the negative 14, divided by the sum of Ka1 plus HA. That all works out to be hydronium, H3O plus, equaling 8.8 times 10 to the negative 7 molar. And when we take the negative log of that, we discover that the pH is equal to 6.06. And so there you have it. H2A plus can be treated as a monoacidic species, A minus can be treated as a monobasic species, but when you have HA in the middle, you have to use this equation. That's it for today.